Hello everyone, I'm Mahshid Alamdar from University of Texas at Austin, and today I want to talk about multivariate artificial synapse with straight node geometry for neuromorphic computing. So let's start with why magnetic tunnel junctions. Emulation of neurobiological information processing by artificial neural networks enables new frontiers in efficiency when performing data-intensive and real-time artificial intelligence tasks. Today's von Neumann computing architectures need to access external memory and also have serial processing, which increases the energy requirement for processing big data tasks. Memory access in modern computers using von Neumann architectures can dominate as much as 96% of their computing time. So the development of magnetic devices could remove the memory wall between computation and memory by implementing reconfigurable logic in memory blocks. Magnetic nano devices have many beneficial features that make them promising candidates for neuromorphic computing building blocks, such as non-volatility, ultra-low power consumption, high endurance compared to other resistive memory devices, radiation hardness, and of course, leveraging of close-to-market MRAM technology. In the brain, synapses, as one of the two main building blocks of neuromorphic computers, control the degree of connectivity between neurons by having multivariate conductance states that can be set based on inputs from neurons. The fundamental requirements of a synapse are the abilities to change and store its states. By leveraging the non-volatility of magnetic tunnel junction, the synapse provides the memory required to store the synaptic weights. But how about changing these states? Previous simulation works have shown that domain-wall MTJ synapses have the necessary characteristic for neuromorphic computing. However, experimental works have only focused on binary domain-wall MTJs, and to the best of our knowledge, no experimental works have studied the behavior of multivariate domain-wall MTJ synapse. To achieve a number of conductance states per device, we use the three-terminal domain-wall magnetic tunnel junction device. As you see in this picture, the heavy metal ferromagnet oxide three-layer stack is patterned into a domain-wall track with a single long rectangular MTJ centered on top of the track. 5 lithographic notches are used to set the domain wall at specific positions along the magnetic domain wall track. The in and clock terminals are used to set the domain wall, drive the domain wall back and forth using spin orbit torque, and the Oersted line is used to electrically initialize the domain wall position. And the 4P and output terminals are used to measure the resistance states. This picture shows the top-down STM image of the real device with 350 nanometer domain wall track width. And this picture shows a schematic of the field full stack. The last plot shows the out-of-plane minor field loop for a synapse with domain wall track width of 350 nanometer, showing perpendicular magnetic anisotropy of the free layer and 16% TMR. Now let's take a look at the switching behavior of these straight-notched synapse. So for this experiment, the device is first set to the anti-parallel configuration using a DC minus 120 millitesla saturating magnetic field. After saturation, a DC minus 4 millitesla bias field is applied to compensate for the offset field loop and promote efficient SOT switching, which could be removed through film stack engineering in the future. And then 50 nanosecond voltage pulses are applied between the in and clock terminals with increasing amplitude to push the domain wall forward in the domain wall track. And then MTJ resistance is measured after each pulse. This figure shows MTJ resistance versus voltage pulse for 10 cycles, each repeated from saturation. You can see 5 resistance levels in this plot, which shows the domain wall is pinned by all 5 notches in the domain wall track. While the resistance of each multivariate level is extremely stable at each respective notch, the stochasticity in switching voltage over the 10 cycles is also observed here. Here, from the spacing dimensions of the notches, we estimated the MTJ resistance when the domain wall is pinned at each notch, which are N1, 2, 3, 4, and 5, as shown in this table. These calculated resistances are very close to the resistances measured for each state in this plot. And here is the state distribution map where the probability for the domain wall to be in a particular notch at a particular voltage is plotted. These 5 regions correspond to the 5 notches on the domain wall track, and the height of the color region is proportional to the probability that the domain wall occupies the corresponding notch. Here we simulate an inference task that takes advantage of the high stability of these synapse resistance levels and is not very affected by the randomness observed in setting the levels. To use the domain wall MTJ for a neural net inference application, the MTJ is programmed to the desired weight levels using a write verify process with multiple pulses to overcome the effects of stochasticity. This is a one-time programming operation and is not needed after the system is deployed for the inference application. This figure shows the measured error over 10 cycles in the conductance, which varies from 0.68 to 2.73 microsiemens for each conductance weight. The average of these 3 conductance errors for the 3 notches below the MTJ is 2.53 microsiemens. So once the domain wall MTJ synapse is updated, the conductance levels are highly precise, and this very high precision is because of the fact that the domain wall is only being pinned at notches that cannot move because there are lithography defined. And this low write noise allows more precise representation of neural networks weights. To show the straight synapse can achieve near ideal inference accuracy, we used cross-sim to simulate analog inference in a domain wall MTJ system for CFAR 100 image recognition task. The CFAR 100 is a collection of images and is commonly used to train machine learning and computer vision algorithms. This dataset has 100 classes, which each containing 600 images of size 32 by 32, and each image is with 3 different color channels. These 100 classes are grouped into 20 superclasses, which you can see in this picture. And this picture is an example of this classification for CFAR 10, which has only 10 classes, just to get an idea how this classification looks like in general. After mapping weights to conductance, a conductance error is applied that is sampled from a normal distribution with 0 mean and a standard deviation of 2.53 microsiemen, corresponding to the measured write noise in our inference plot that we had in slide 5. This figure shows the CFAR 100 inference accuracy as a function of the number of available notches in domain wall MTJ. At least 16 notches are needed to obtain a reasonable high accuracy on CFAR 100, which is because of the neural network's intrinsic sensitivity to weight quantization. Here we compare the ideal domain wall MTJ device with no conductance error in blue and domain wall MTJ device with the experimentally characterized level of conductance error in orange. These curves are almost lying on each other, which shows that the write noise in the measured domain wall MTJ device is negligible. We also noted that the conductance error is based on the properties of a single device and does not include the effect of device-to-device variation. So to understand the effect of device-to-device variability, we also performed the inference task with a write noise that is 10 times larger than the measured value, which is shown here in orange dashed line. This figure shows that with this higher write noise, the accuracy has degraded, but it is still well above 0. And this suggests that the measured level of domain wall MTJ write noise is well beyond what is sufficient to obtain high accuracy on CFAR 100. So now, as a conclusion, we showed a straight notch domain wall MTJ synapse in which by fabricating lithographic notches in domain wall track, we could achieve stable resistance states that could be repeatably controlled. We also showed that this extremely low read noise produces excellent inference performance compared to other synaptic devices. Furthermore, the fact that the switching behavior can be statistically analyzed, making it potentially useful for stochastic neural networks. All these properties make multi-way domain wall-based synapse a feasible technology for neuromorphic computing, which can be more effectively capturing the functions of the biological brain than traditional technologies. And finally, I wanted to thank all my colleagues at INC Lab of UT Austin and also our collaborators at Sandia National Labs. This is my email address. I would be happy to answer if you have any questions. Thanks.